flame that burns around 5,700 degrees, produced by a burning more acetylene than oxygen, and can be recognized by a greenish feathery tip at the end of one cone. Okay, that is a carburizing weld. Also referred to as a reducing flame because it tends to reduce the amount of oxygen in the iron oxide. Okay, so that is the temperature for a carburizing flame. All right, oxidizing flame temp. Everybody ready? Here we go. Oxidizing flame temp, 6,300 degrees Fahrenheit, is produced by burning an excess of oxygen. It takes about 2 parts oxygen and 1 part acetylene to produce this flame. It can be identified by the shorter outer flame and the small inner white cone. Hey, are you okay?
I just made him into a walk.
I thought you Army guys were used to bugs and stuff, man. Now, Sam would be the one I'd be worried about. Because the Air Force guys, they actually give them real nice places.
I haven't done anything dangerous yet.
It's a sword subject.
All right.
No Cinnabons for us.
Normal flame, normal flame. Normal flame is 5,800 degrees or 5,850. Not that anyone goes and shoots a temperature gauge on the end of your flame. Like, oh yeah, that's the 58. There we go. But hopefully by looking at the color or discoloration, be able to tell if it's more oxidizing or carburizing. I'm almost said acetylizing, but carburizing. At the tip of the inner luminous cone is produced by a balanced mixture of acetylene and oxygen supplied by the torch. This flame is used for most welding because it does not alter the composition of the base metal. But that's not always true, because with oxygen and acetylene, it's highly dependent upon how close you are with the torch. Oh, you start getting the puddle moving, and then all of a sudden you get too close, and it blows a puddle everywhere. No! Tears, weeping, tears, weeping, tears. Or you get too close, and it blows the flame out. Boof! Right after you've got it perfect. Another blessing of MIG and TIG that the flame does not normally go out. Okay? I didn't say it won't. Notice that. Because about the time you're getting really good at TIG, you touch the TIG tungsten to the metal, and then all of a sudden it's like, and it welds itself into the metal. You had a really good weld going until then. So, TIG, you actually do not touch TIG. So when you think about TIG, think about 2 arms going with a pedal. Okay? All right? Yeah. It's like, you know, one of those deals. So, all right, you're welding. Okay, you got so TIG, you're not actually touching the arc to the steel metal. Okay. It'll jump a gap about that far. You want to be about that far above your material. Well, the same kind of idea with gas welding. You don't want to be all the way down on it with your torch. It'll blow your flame out. Or it'll cause a hole to China. Okay? And so you want to be just slightly above it, and you want to be kindly making circles so that you can, why don't we make circles, small little circles with our torch? While you're adding rod. Even heating, even heat distribution. Nailed it. Good job, guys. All right. So normal flame, we want to smoothly move that heat around so that we can get a good penetration all the way around whatever we're welding. Okay. Sometimes I get too far back. I'll back up too far and I get a cold weld. Cold weld. Cold laps, cold weld, they don't go all the way through. They're really, really rough edges, probably more than even that. There's insufficient heat, rough and irregular. Edges are not feathered smoothly to the base metal. Here's one that I took a picture of. Womp, womp, womp. You know what? material. They did paint it to hopefully cover up some of the scents. But, see how the glob is kind of like way up here and not feathered out? That is a cold weld. That is like, all right, ready, set, go. Boom! Slap it on there, okay? So they did not get very good, even heating around this exhaust pipe. Okay?
So you just need to go slower so it has time to heat it up.
Slower, yep, correct. Slower and probably a little wider pattern with the torch. Correct. But what did they do here? Right over the top of another weld. Is this standard practice? What's standard practice in aviation?
Grind it off first.
Grind it off and re-weld it. This is standard practice in tractor, farm machinery, right? Just weld back over it. But standard aviation actually requires you to remove all of the weld material. Okay? Should you do that on anything? Yes. Can you do that on everything? Not. Sometimes you can. But yeah, the best thing to do there is to remove the material and re-weld it. All right, excessive acetylene, the puddle begins to boil. Okay? Slight bumps along the center, craters at the finish. Okay? Why would the crater be at the end of the fillet weld? That, and there's no more metal to absorb the heat. So what happens is as you're moving that torch along, now you're like, it's going to, whatever the last bit of metal is absorbing the rest of that heat from the torch, and it can't dissipate it to the rest of the material. So it's going to take it up and end up blowing craters, which make the pockets and very porous, very holy, in this case unholy, but holy material. So what happens with porous material or holy material? What could be a potential problem with that? Corrosion. Moisture, it will trap moisture and cause corrosion. Good. A bad weld. A bad weld will have, looks like the angry caterpillar here, where it has irregular edges, penetration variation, where if you were to look at the back of the weld, if you flip this over and you look from this side to the material here, you'll see a discoloration as it goes along. You'll see, okay, it's real wide here, and then real narrow, real wide, real narrow, all the way with the bluish color, okay? So it can be irregular. Here is a really bad weld. Well, it is welded, but it seems like it has more holes than welds, doesn't it? Okay, we notice, look at the color distortion here. What do you notice with the color distortion? Say what?
Even.
Kurt, what were you saying?
I didn't say it.
Who says?
Colors.
The colors, okay? So you've got pretty good heat here, and then I don't know where we didn't get heat into this material, but we sure did get heat on this one. Yep, the heat was right here, okay? So they were like, oh no, bring the heat back, and they get the material here. So, very inconsistent heating, okay? All right. Oh, you're grinding that one off. You're not filling that one.
No.
This is not machinery, yep. Oh, yeah. To start, it may be poor, would you say craftsmanship? Yes. But it's definitely a poor fit. Good. A beautiful weld, here we go. You want to see what a beautiful weld is? Here is an oil cooler style. And look at that. Slightly inconsistent still, but aluminum weld is not for the faint of heart. Okay? You can see some inconsistencies here, but very good, consistent weld there around the connection to it. All right, this is, if all of you at the end of the year have a weld like this, okay, that's perfection. I mean, it's like, whoa, just beautiful.
At the flattened caliper.
Yes, Zachary?
So, and the kind of matte silver on each side, that's the heat from the heating of it on the metal?
Oh yeah, more than likely. I can't really see what the material is here. Was that a butt weld or was that, looks like a butt weld. All right, here's a really difficult weld with an exhaust pipe. Whoa, whoa, really hard. And it's really hard when you get to these angles like that, and as Kurt just mentioned, especially the amount of distance you're going to cover. Because right here was really wide. See that? And then they had to get real narrow as they're coming in here. Okay? Really difficult weld.
You're right.
Especially on stainless like this one. It's extremely hard. Yes, sir.
So when you're welding, does it have to be all in one run? Or you have to pull off and readjust?
Okay, so you want the best, you want it to be as consistent as possible. If you can get it in one run, yes. Is that possible? No, it's not always possible to get one run. Man, if you could get it in one run like this one, there's no way. I mean, I don't know how you get all the way in the circle. Okay. All right, is this one still in your book, this picture? I think they may have removed it from the airframe section, but if it's still in airframe, it's a pretty good picture, I think, actually, of what a stick weld or a bad weld would be, okay? A good weld, you notice pretty even coloration here, doesn't have these like craters going through it, okay? Real nice smooth weld. If it's like this here, you're way too fast with your weld. Too slow. Notice the discoloration between this one here and the top one. Notice too slow. Okay, going too slow, it's spitting and coughing and throwing up here, and then this one's nice and smooth, okay? And the color is pretty consistent. Here, your arc too long, okay, super wide, hideous looking. Amperage too high. Now, amperage too high, what's going to be the byproduct or the end result of an amperage too high? Way too high. Yeah, it's gonna weld it all the way to the table. If you wonder why our tables in there have welds still on them, it's because the metal on top of it was welded to it because the amperage too high. Amperage too low, you have officially put a really nice consistent weld on it with no penetration. Any questions on that? I feel like it's a pretty good picture what you're looking at. All right, so pour welds must be cut and ground away. There you go. Don't send it, don't glob over it. You know, there's a saying that says, bigger the glob, the better the job. Bigger the glob, the better the job. No, don't make it piled up. Not a better job that way. Grind it off and redo it. Do not weld over an old weld. Okay, this is not your tractor, okay? A crack adjacent to a weld indicates that the weld has cooled too quickly. So if it cracks just on the other side of it, potentially got too cool. Okay? Please don't go pour water right on top of your weld after you've welded it so you can touch it. Why? What's the problem with that? It's going to cool it too quickly, which is going to only cool the surface and crack the surface. Yeah. Good. So, ways to check a weld if you had to. You could do a visual. Bam! Your eyes. Okay? You could do magnetic particle inspection. You're saying, well, what is that? Well, congratulations, you're all going to do it this next week. You could do a liquid penetrant where you spray this really cool fluorescent stuff on it. We're going to do that next week too. And then put it under black lights. So you're all going to be under black lights next week as well. And see if it has surface defects. If you're still not sure how good the weld is, you could do an ultrasonic inspection and be able to send a sound wave and see how it responds back. And it actually, the ultrasonic machine would read that weld. If you don't have any of those, okay. What is brazing? What is brazing? It's a fabrication method of thermally joining metal parts by wetting the surface with a molten non-ferrous alloy. So, fuel tank repairs. You don't really want to weld and penetrate all the way through a fuel tank. Make sense? So how do you repair a fuel tank repair? Usually with brazing brass. You'll braze the outside and put something, a material like brass, along the edge to be able to hold it, okay? Materials melt at a temperature higher than 800. Notice the temperature difference there. When I'm welding, what temperature range am I in? I'm over 5,000 degrees, right? Here, I'm roughly 1,000 degrees, okay? Lower than the melting temperature because we do not want to hit 2,600. Nope, you do not want to hit 2,600 degrees Fahrenheit. Now that's not standard, okay, depending on what is in it, okay? For example, if I have a lot of nickel, Shane, I have a lot of nickel in my material, what would that indicate?
It's stainless steel.
A stainless steel derivative, yep. And so it's going to be more temperature resistant, okay? So that's not always true, but we do, 2,600 is not fast and hard number, okay? But roughly somewhere around 2,600 is the melting point for steel. Yes, sir?
Brazing, this sounds awfully like soldering copper, just the same.
Good. So soldering is even cooler than that.
Okay.
Soldering, if I'm not mistaken, is somewhere like 400 to 600. And then we're above 800 here. So once you get 800, you're in the whole nother level of brazing. Okay? You're still using a torch, but a very cool torch. Brazing's very quick, fast. You don't use a torch with soldering. I mean, you could use a MAP torch or propane torch, but you're not using an oxygen acetylene torch unless you want to cut the copper. All right, so we already talked about how this is any different, okay? Oh, here's my cute little note. Okay, temperature range for brazing is 900 to 2,200 degrees Fahrenheit. Okay, everybody good there? It's interesting that brazing can be used for dissimilar metal connection or joining. Why is that? James, why can we use brazing for joining two dissimilar metals? Because you're not breaking down their structure. Nailed it. Good. All right, just for Shane, I put this one in here. Soldering below 800 degrees Fahrenheit. Boy, I'm glad I got that one right. All right, fabrication method of thermally joining metal parts with a molten non-ferrous alloy that melts at a temperature below 800. Everyone see that? But we still want it to, when it cools and hardens, it forms a strong leak-proof and hopefully good conductivity. There's your electrical term for the day, right? We want good amp flow.
Okay. Right.
He just got all right. Okay, all right. So what is welding? A fabrication process that joins material, usually metals or thermoplastics, yeah buddy, by using high heat to melt parts together and allowing them to cool, causing fusion. Ooh, you lived in Sudan? Is that correct?
Yes, sir.
All right, did you ever get in a fender bender?
In Sudan?
Yeah.
No.
Oh, that's boring. All right, so I've had a few, you know, because we have like, you had like 7 million people, and then you had, you know, you have bikes, and the bikes don't have any rules. So if they want to ride on that side or that side, that's fine. And so, you know, you have all these little motorcycles going around you, and of course, they'll bump into you, and they'll say, "Oh, sorry, oh," and then keep going. So they would take like a torch, and they would stretch plastic, and they would remake your, like, oh, is it red? They'll take a red plastic and melt it to make a tail light. So they're sitting there stretching it, and they'll get these, like, they'll stretch it all out, and then, oh, you want lines in it? They'll put the little lines with, it's super cool. So that was a type of welding that they were doing with a torch, but they would stretch thermoplastics pretty wild to be able to make your headlights and taillights every time a moto decided to bump into you. So, I'm not salty about it, I just thought it was really cool. All right, so welding is hotter than brazing and hotter than soldering. Soldering. All right, everyone clear with that? All right, inspecting a fillet weld. Fillet weld.
The objective of this job practice is to advance skill in T-joint welding and to perform a practical test providing measurable standards of acceptability. Follow the usual procedure steps. Use proper clothing, tools, and eye protection. The materials and power source settings for this exercise are listed in your workbook. Set the power source to correct current and polarity. Position the plates on the work table to form a T-joint. Offset the vertical plate from the center of the flat plate by about 1/2 inch from the edge. Tack weld the joint on the ends to avoid interference with the weld bead. Deposit the bead on the short side of the joint, angling the electrode 45 degrees from the vertical plate and 5 to 10 degrees in the direction of travel. Use the whip and pause motion to make a bead with leg dimensions equal to 3/16 inch. The face of the fillet should be approximately flat. Break and re-strike the arc at about the halfway point to test your restarting and tie-in ability. Be sure to make the bead full size at these points to avoid critical weak spots. When the weld is finished, cool the workpiece in water to make it easier to break, and visually inspect the completed weld. The standards of acceptability are: the weld shall be acceptable by visual inspection if it shows that the weld has no cracks. The weld must show complete fusion between the weld metal and base metal. There shall be no slag inclusions exceeding 1/8 inch in any 6 inches of weld. There shall be no porosity exceeding 1/16 inch maximum, and the weld shall have no more than the combined total of 1/8 inch in any 1 square inch of weld. The weld shall be acceptable if undercut does not exceed 1/32 inch in width, 1/32 inch in depth, and has no more than the combined total of 2 inches of undercut in any 6 inches of weld. Bead profile. The fillet weld should be flat to slightly concave with equal legs approximately 3/16 inch long. The face should have a smooth, even contour. The break test, or fillet weld soundness test, should be performed with all protective clothing still on. One method is to place the workpiece in a press and squeeze it until it is flattened, or the piece can be broken or flattened by using a hammer, but only in an area where bystanders won't be hit by flying pieces. The break should be through the center or throat for the entire length of the weld. Call the instructor to inspect the weld. The fractured surface of the weld shall show fusion to the root of the joint and shall exhibit no incomplete fusion to the base metal, and there shall be no inclusions or porosity larger than 3/32 of an inch in greatest dimension.
All right. Okay, so review. What's wrong with alpha here? Say what, Sam?
Too much oxygen.
Okay, too much oxygen, but it was a hot well. Okay, there's not smooth at all the way to the bottom here. Okay, Bravo. What's wrong with Bravo here? Cold. How do you know it's cold, Zachary?
Because it doesn't penetrate all the way through and it has a really high crown.
Okay, good. All right. Let's see. Chris, what's wrong with Charlie here?
The crown it's all like jagged.
Good. All right. Good penetration, but not a smooth over the top contour. Okay. And then what's wrong with Delta? What's wrong with Delta?